So hi everyone. Today I'm going to talk about some problematics which are related to networks and my fields of research, which is voting. So indeed, it's not everything is simple when we vote in networks. For instance, in 2009. There was a lot of users of Facebook who were outraged and accused the social network of claiming too many rights over user-generated artist content, for instance. So in response, Facebook organized the votes in its network to choose the new term of service, term of use of the website. And they said that they must be at least 30% of the active user who should vote for the results to be binding. The new rules proposed by Facebook were approved by a large majority. However, only 0.3% of the users actually voted. They still enforce the new terms of use. So in this example, we can see that voting require time and dedication. And there was some work proposed to use the structure of the network to make things much easier. For instance, with the use of what is called a liquid democracy and other ideas. So this is an example of a problematic which links networks and voting. So in this talk, I'm going to present the answer to this problematic, which is basically the liquid democracy, and how it is used, for instance, first for electing a representative, like a representative on a network, like a real election. And in the second time, so the full last part about judgment aggregation in a network. So using the structure of the network to vote on a proposition or motion, like in the Facebook example. So first, let's see what is called liquid democracy. So in a classic proxy voting settings, so here in this network of platypus, which is the animal of the links, in classic proxy votings, a voter can transfer his voting power to any representative, so a friend in the network. So, for instance, this is a delegation graph in which this platypus delegates its vote to this one. This platypus delegates its vote to this one, and this one vote for himself. This one vote for himself too. So in the end, the weighting power of this platypus is 4, the weighting power of this one is 2, and this one has a voting power of 1. Now what is interesting is that we can maybe transfer this proxy. For instance, if this platypus says that he wants to be represented by this one, and this one don't want to vote either and delegate its own vote to this third platypus, then the voting power of the final platypus is 5, because it's the number of like the number of paths which end with this platypus. So I hope this is clear. So it's like proxy voting, but we can transfer our own voting, proxy voting power to our representatives. But there can be issues with this model. For instance, if two nodes mutually transfer their voting power to each other, there is nobody at the end of the chain, and there is no great representative who will vote for everyone. So how can we handle such cycles in the different settings we are going to see. That's what we are going to see today. So first, can we use this model to elect representative? That's what is presented in the paper Voting in Social Network by Paul and all in 2010. So I'm gonna present it a little bit. So here we want to elect a node of the network as the representative of the network. So we have the delegation pass, as explained before. And the score of every node will be actually the number of directed paths ending or going to this node. So for instance, the score of this platypus is 2 because there is two nodes who delegate their vote to him or who vote for him. And this one will be 6 because there is all this tree, all the people in this tree who vote in the end for him. So up to now, it's pretty clear. But what Paul Baldi asked in this paper is, how much do you trust your friends and the friends of your friends and the friends of your friends? So actually, what they assume that trust decays with distance. That's why they introduce a damping factor. So the score, instead of being the number of paths going to one node, will be for each path going to the node, the longest is the path, the lowest will be the score associated to it, because it will be alpha power the size of the path -1. So it's just a constant to the -1, but so the longest is the path, the less we trust the final representative. And so we can see that a large damping factor indicates more trust in your connection, and a low damping factor indicates that we basically only trust the person we are voting for, but not its own connection. So, for instance, if with a damping factor of 1/4, the scores of these two nodes. So before the score of this node was 6, so it was the winner. But if with a damping factor of 1/4, these two nodes are both winners, because the score of this node is 3, the score of this node is 1. And if we do, so there is 1 plus 3 times 1/4, which is 1, plus 2 direct child, so it's 3. And these two nodes have the same score, so they both winner. And if we lower again the damping factor, this node is the only winner. So basically it says that when the damping factor is low, only the direct child of the node counts. So we basically just count how much people directly vote for you. So they okay. So maybe you are thinking, yeah, I know this. It's PageRank, and indeed, in the paper they just use exactly the PageRank algorithm, but instead of pointing to multiple other nodes, each node only select one node in its neighbor. So this is a PageRank of a node in a classic graph, and here we have a term which is the branching of paths, which if the path is the first node, the second node, etc., until the k+1 node, the branching will be 1 over the number of out neighbor of the first node times 1 over the number of out neighbor of the second node, etc., until the last node. But here there is only one out neighbor for each node, because each node only votes for one person. So the branching path will be equal to 1, and we find alpha to the power p, which is exactly this, exactly the same thing than before at a constant. Yeah, there's just a constant which is different. So PageRank in our model will be a setup in which each node can vote for several friends and divide its voting power equally among them. Okay, so in the following of the papers, they prove some properties about their model in the case of large dumping and of low dumping. So if we have a large dumping, that means that we do not trust the friends of our friends. Then they say that for a sufficiently small alpha, the vote of every node can only influence the victory of its representatives. So in the paper, in this talk, we are going to call them guru because it's easier. So the guru is the person to whom I give my votes. So for instance, here, node X has K direct child, and node Y have only one child. So the score of X will be K, and the score of Y will be 1 plus alpha, the dumping factor, times K. And Y only win if alpha is greater than 1 minus 1 over K. So alpha need to be large for Y to win. So this is an example to show that only in the case of small alpha, only the direct child will influence your victory. In the opposite, if we have a large alpha, all the winners will be on the top of some tree. So indeed, everything looks like a tree in this, or almost like a tree in this delegation graphs. For instance, we have something like that. So this platypus delegates its votes to this one and this one to this one. And the score of each platypus on the top of tree will be the size of the tree. So this is this one who win because the tree is of size 4, and all other trees are smaller. But what happens if we have a cycle on the top of such trees? So first, note that a cycle can only happen on the top of a tree, because so a cycle can only happen between what we call great gurus. So great gurus are nodes which do not delegate to another node. So if we are a guru cycle, because if the cycle is not a guru cycle, then that means that there is one edge which go in the cycle and one edge which go outside the cycle, which is not possible because each node only votes for one other node at most. So in this case, what happened? This node can still be winners, but actually, what do you think? Who do you think will win? And this will be this node here, because they show in the paper that the score, the winners of the election will be other nodes on the cycle, the top cycle, which belong to a component with the largest average tree size. So for instance, here, the average tree size is 1 plus 4 plus 2 over 3, which is 7 over 3, which is less than the size of this tree, which is 3. Too much 3. So this is this node who win. And we can think of it as we divide equally the power of each node in this cycle. This is when alpha is close to 1. Okay, so this was the use of liquid democracy to elect representative with this first paper. And now we are going to see something different use of liquid democracy, which is far more used in real life. So it's a judgement aggregation. So I use a paper from 2017. So I present a paper from 2017. So here we have a bunch of proposition, P1, P2, extra until Pk. And each voter either approve or disapprove a proposition. So that means that to each user I, we associate a function phi I, which associate each proposition to either 0 if he rejects the proposition, 1 if he accepts the proposition, and asterisk is in the case of abstention. So it doesn't know or doesn't want to vote. So basically each voter gives its opinion on each proposition. And then we use an aggregation rule, for instance, the majority rule, to select whether or not the proposition is approved in the end. So for instance, it's the example of the beginning. Do you approve the new terms of use of Facebook? So there is more yes than no. However, there is like 1 million people who didn't vote. So once again, we can use the liquid democracy or the structure of the network to make things better and count the vote of everyone. So for this case, for each proposition, either I vote myself, or if I think I can't really give my opinion on this topic because it's too complicated for me, or I'm not a specialist, I delegate my vote, for instance, to Francois if I think it's knows more the topics than me, if he's specialized. And he's going to represent me. So for each proposition, every user will choose a guru, so a representative, and this can be herself. So if you vote yourself, then you don't need a guru because you already vote. And this gives us, again, a delegation graph. And I called, so guru is a term used in this paper. And for the users which are on the top of, on the end of each pass, that means that they don't delegate their votes because they vote themselves. I call them great gurus because they represent a lot of people. And in the second time, we want to propagate the vote of the guru to their followers and apply, for instance, the majority rule to determine whether or not the proposition is accepted. So let's see this in an example. Here we have a network, so with a small connection with thin edges, and thick edges like this represent a delegation. So here there is three great gurus, which are these three platypus. So they each vote. For instance, these two accept the proposition and this one reject it. We propagate the vote to their followers, so like that. And we apply the majority rule. So here the proposition is accepted. So it's pretty simple right now. And this concept is used, was used at least in several experiments. For instance, liquid feedback is a software that is used for political opinion and decision making, and was used, for instance, by pirate parties in Europe. And there was also experiments on Google with Google Votes. And I think there is a small county in Germany who try to use a liquid democracy to accept or not proposition, but it didn't work a lot. And I don't know if it's still used because I think this was like popular some years ago. So, okay. We saw that it is easy to do an election with this, but once again, we can have problem with cycles. So, for instance, these two nodes both delegate their vote to each other. So this one delegated vote to this one and this one to this one. And what the liquid democracy software do in this case, it basically ignores these voters. So we only take into account the voters for which there is a great gurus who voted. And here there is only one, and the proposition will be rejected just because we ignore the vote of all these people. And what Christophe and Grossi said in this paper is that it's by ignoring these voters, we drop the nice one man, one vote properties that liquid democracy can bring. So that means that everyone can vote in the can participate to the voting process, even without taking the time to see all the proposition. And they also show that if each proxy voting profile is equally probable, the probability that every voter abstain, so there is no vote at all, is strictly greater than 0. That means there is not null probability that everybody abstain, which is not a really good property. So they suggest a slight modification of the process, which is not complicated. It's basically that instead of just voting a trustee, a guru, we also cast a default vote, a substantive opinion, in case we are in a cycle. So, and then for each, so once we have casted our substantive opinion, for each guru cycle, we will take the majority opinion among the cycle and propagate it to their followers. For instance, in this network, everyone cast a default ballot, which is represented here, and here there is the cycle. Hopefully they both accept the proposition. So they will. If we apply the majority to this cycle, it will return accept, and we propagate that they accept the proposition, and all their followers will also accept it. And we saved it. We still accept the proposition even with a cycle. However, you may notice that we can have that when there is an equal number of people who accept and reject in the cycle. So for instance, this node accepts the proposition and this node rejects it. So in this case, we will propagate that the cycle abstain, but only in this case in which we have an equality in the guru cycle. Okay, so now that we know the vote of everyone, so how in a decentralized network in which a node can only communicate with its neighbor and potentially don't know who is its representative, its great guru in the graph, because it can be like a 5 steps away. How can a node retrieve its vote? At the time of the election, great gurus voted, and we want to propagate this vote to all their followers. So go down the whole tree. In this paper, they suggest a pretty obvious process that they call Boolean degrowth process. And it's pretty straightforward. So if we note OI of P at time t, the opinion of voter E on proposition P at time t. So at time 0, every voter initialize its opinion with its default vote. And at time t plus 1, it just retrieves the vote from its direct guru, like its direct representative. And this goes down the tree like that. So it's pretty easy, right? However, it stabilizes if and only if every cycle in the graph is unanimous. For instance, here this cycle is not unanimous, so this node will retrieve the votes of its direct guru, which is this node. So it will turn green, but this one will turn red at the same time. And at the next step, this one will turn red again, and this one will turn green again, and etc., etc. So it will not stabilize. And they also show that it stabilizes in less than diameter of the graph steps. It's basically because we only need to go down the largest path between two nodes to propagate the vote. And I thought that, okay, this process is interesting, but it doesn't stabilize. So maybe they will propose a better one. Also, they propose this process. It seems a bit obvious, but actually, in the paper, it's more complicated than this, because they associate it to some logic properties. There is like a logic formulas behind that I didn't need it in this presentation. So it's what makes it quite obvious. So anyway, wait.
Just a question. So do you mean that they do real judgment aggregation in the sense that they have several proposals to decide upon, and logical connection between these proposals, or?
Yes, that's it.
Thank you.
Yes, so there is a logical, so each, in this paper, each node has its own logical dependency between different proposition. So basically, they say, so if I accept proposition 1 and 2, then I need to accept proposition 3 and things like that. So it makes things a bit harder because they need their different gurus to send a good, something consistent with their own logic. But I don't use it here. So this process does not stabilize. So, and I found that the unanimity constraint was a bit strong. So I propose another process. And the intuition behind this process is that every guru cycle will, in a decentralized way, apply the majority rule among them to determine their votes, and after that propagate this vote to their followers. So maybe I can explain how it works. So the idea is that if you're in a cycle, so the idea is that at the beginning, you will send a message with your vote and your ID. And this message will go through the graph. And if it goes back to you, then you know you are in a cycle. And then you can, on your own node, compute the vote of the cycle and propagate it afterward. I don't know if it's clear. I'm going to explain in more details. So at time t0, great gurus, which are on the top of the chain, will send the pair vi with their votes and star. So star means that it's the vote of the great guru, so you have to follow it if you receive it. Okay, and other nodes, which are not great gurus, so who do not delegate, the nodes who delegate their vote will send the pair with their votes and their ID. And at the same time, each node initialize a count, which will be the count of votes of the cycle if they're in the cycle. So they initialized it with their own vote. Okay, so at a time t, the node E will receive a message from its guru, a message with a vote and an ID or a star. So if the message is a star, that means that the vote comes directly from the great guru, and the node has to follow it. So it just takes the votes and say, okay, this is now my vote, and propagate the message to its follower to say, okay, you have to vote to do this vote, to vote yes or no, depending on what the great guru votes. And if it's not a star but the ID of a node, then if it's not its own ID, then we increment the count with the vote it received. And if it's its own ID, that means that I, the node in question, is in a cycle, and it can compute the average votes of the cycle, because with the first case and with the count, it computed the total number of approval votes in the cycle. And so it can compute the opinion, the aggregated opinion of the cycle, so with majority rule, for instance, and send the results to its own followers. with a star in the message, because now it knows that it's the final vote. Okay. So this is the second the new process I propose instead of the one they use. And what is nice is that this process will always stabilize after at most diameter of the graph plus one step, so it's basically the same. However, in the previous process, we only needed to transfer 1 bit in each message, because we only needed to know if our representative or guru approve or disapprove the proposition. And here we need to send messages of length log of the number of nodes in the graph, because there is the ID of the node in each message. So it's a bit it's longer messages, but since the process always stabilizes, it's maybe the price to pay. And also each node can stop sending and receiving messages once it receives a star, because it knows that it is his final vote. So it don't need to retrieve messages from its guru anymore. Now we're still in the decentralized network. Each node knows its own vote, but we want to compute the result of the votes in a decentralized way using majority rule. So we have the whole graph like that, and we want that in the end, every node turn green because there is more green than red in the graph. So this is just the propagation of the result of the election in a decentralized way. So how we can do it? Maybe some of you already know this. We use a distributed averaging algorithm. So the first one I'm gonna talk about is published in 2007 and it's called quantized consensus. The idea is that we initialize the nodes which approve the proposition with a score equal to n, the number of nodes in the graph, and those which disapprove the proposition with a score of 0. So the average of all the scores will be equal to the number of approving nodes, because if, let's say, there is k approving node, the average will be k times n, because the score of this node is n, plus n minus k, so the number of disapproving node times 0, so it's 0, over n, the number of the total number of nodes, so it's k times n over n, so it's k. So the total, the average of every score is equal to k, and we want to propagate this average, and that in the end, every node, the score of every node is precisely k. That will mean that everyone knows the average, and so if we know the average, we know if it's more or less than 1/2, and we can apply the majority rule. Okay. How the algorithms do it, I'm not gonna present it entirely, but basically, at each time, two neighboring nodes can communicate, and if they communicate, they can swap or change their values to the average of the two nodes, basically. So from time to time, two nodes will take the average of their scores, and in the end, every node will have the global average of the network. So taking the average will ensure that at each time the total score is equal to the initial score, and that they prove it in the paper, but ultimately each node will know the average of all nodes and then the result of the voting. So an example, if two nodes communicate, so the first node has a score 25 and the second node has score 4, and they communicate to take the average. So here, 25 plus 4 is 29. So the average is 14.5. So there is one node with 14 and one node with 15. And what is important in the algorithm is that the node with the greater values after the swap will be the node which had the lowest values before the swap. So here it has a lower values 4. So after it will take 15 and not 14. Okay, so this is a quantized algorithm process, but in 2009, so this algorithm require to send and receive messages of size log of n the number of nodes in the graph, because the maximum score is n. But in 2009, so 2 years later, there was another paper which says we don't need to know the exact average if we do a majority rule. We just need to know a gossip. So a gossip like, okay, I heard that the average is greater than 1/2. So I heard that the proposition is accepted, or I heard that the average is less than 1/2. So the proposition is rejected. And with such a gossip, we only need to propagate a small number of bits, so basically two bits, which is far less than log the n, so it's great. And how it works is very similar to the one we saw before. So there is 4 states. Nodes with 0, we start with, they say, okay, disapprove, fully disapprove, 1 is fully approve, and 0.5 minus means I heard a gossip that it's less than the 1/2, so it's the majority disapprove, or 1.5 plus means I heard that the majority approves. And at each time t, neighboring nodes, once again, will can communicate and exchange their state according to this figure. So basically, if there is 2 nodes with one node which is 1 and one node which is 0, they cancel each other because in the end, there is only 0.5 plus and 0.5 minus. And the idea is that the difference between the number of nodes with 1 and the number of nodes with 0 is always the same. So in the end, for instance, if in the beginning there is 100 nodes with 1 and 105 nodes with 0, in the end there is only 5 nodes with 0 and 0 nodes with 1, and all other with 0.5 plus or minus. And once we have only 0 or only 1, if there is only 1, for instance, they will convert every other node. So for instance, if there is a 1 and a 0.5 minus, then the 0.5 minus become a 1 and the 1 become a 0.5 plus. So they converted to think that the majority approve. Okay. so some properties about this algorithm. The algorithm converge if the algorithm converges and the graph is connected. Every node have state 0 or 0.5 minus if the position is rejected, 0.5 plus or 1 if the proposition is accepted, and in case of ex aequo, everyone have 0.5 minus or 0.5 plus. And their theorem in the paper is that the algorithm converge in time less than infinity with almost surely. So it's good because it will converge, but it's like probability almost surely, so it can be weird.
Théo,
Vas-y, Fabien.
it seems that I may be wrong, but from the figure you show, doesn't 3 states is enough?
3 states?
Yes, just 0, 1, and neutral, because based on seems that but I may be wrong.
I think it's not enough because neutral nodes need also to. So if a node has a neutral plus, then it knows that the majority approve, and if it's only neutral, like neutral, it doesn't know if the majority approve or disapprove, so it doesn't know the result of the vote.
Yes, but I was watching your theorem stating that in the end you've got 0 or middle or 1, and if you have only middle, then it was okay. And it seems that this theorem should still apply if instead of having middle being 0.5 plus and 0.5 minus, you just have middle again neutral. It seems to me that as the interactions are the same, the theorem should apply.
Fabien, I think that yes, but here you have the additional property that in the end, the nodes that have a neutral value have information about the fact that is accepted or rejected because it's a neutral minus.
Exactly.
Okay, I get the point.
That's exactly. Thanks for.
But I have another question. Do the nodes have a possibility to know when the algorithm has converged?
That's the issue. So I didn't dig. I didn't have time to dig a lot in the bibliography, but in this paper they don't propose, or I think maybe I'm wrong, but they don't propose a way to know when it's converged, and they can be heuristic, but in the end, since the probability, we only know that the probability it's almost surely converging in time less than infinity, so it can be very long, and it can happen at the other end of the graph. So we don't really know, actually, I think.
Yeah, from the point of view of one node, I have the feeling that you never know, in fact, when you have the final answer.
Exactly. Maybe you can put yourself in sleeping mode and stop talking to your neighbor if it's always you're always receiving the same message and waiting for someone to reach you. But I think you cannot be sure at like 100%. Okay. Is there another question? Otherwise, I'm gonna present a little bonus. So I wanted to test this different algorithm in a decentralized network. So I created a voting procedure. I proposed a voting procedure. So first, every node chooses a guru among all its neighbors in the network. And they also cast a default vote. In the second time, we propagate the vote in a decentralized way with the process we've seen before from gurus to their followers. And finally, we use the gossip algorithm to propagate the result of the vote. So for this little funny experiments, I used the Velib station dataset. So this is all the Velib station in Paris. I connected them based on distance, so to obtain a network. So basically, two stations are connected to each other if they are at a distance less than 700 meters, I think. So this gives us this nice graph, nice network. And we also create a delegation graph. So this delegation graph is based on the principle that if you have more neighbors than all your neighbors, then you vote yourself, and otherwise you delegate your vote to your neighbor who have the maximum number of neighbors. So basically, a central station will have all the powers. So here we see the gurus highlighted. So for instance, this is the gurus at Châtelet, at la Place de l'Étoile. I don't know, I don't think it's Place d'Italie, but okay. So this is the delegation graph. Now each node casts a default vote. And we can see the vote of gurus. So this gurus vote red, and this guru vote green, for instance. So this is, I don't think this is the vote I used in the video I'll show you, but so this is an example. So I use probability 1/2 for either accepted or rejected proposition. Then I create an environment with a SIMP that was presented by Thomas 3 weeks ago in the seminar, and I launch the simulation. So up. So let's see how it went. So this is the vote of the guru, of the great gurus, like the one who do not delegate their vote. And then this is the vote of everyone, the default vote. And in the beginning, we just propagate the vote from gurus to their followers. So it shows we have this nice map in which like there is like a large cluster of green node and red node. And here we can see that at time 12, everyone, almost everyone already knows its own vote, so receive its vote from its guru. And here we have a majority of accepted opinion which accept. So in the end, the map will turn green, but let's see it in action. So we have this nice rive droite versus rive gauche situation in which rive droite accepts the proposition and rive gauche rejects it. And after like 200 steps, almost everyone knows the results of the election, of the vote, sorry, it's not really an election. And after 300 steps, so everyone, almost everyone, so there is still some not convinced nodes, some red dots which go through the graph. And also there is some disconnected components, so components which are not connected to the main graph, I don't know, at La Défense or even farther, who maybe will never know the result of the vote. But this can be avoided if we ensure that the graph is connected. Okay. Thanks for your attention. And if you have any question, please ask.
Maybe I have a question, several questions, as a matter of fact, about the Christophe and Grossi model.
Okay.
So the first one, sorry, maybe it's not about that, but first question about the averaging algorithm, where they start with the total number of nodes in the, this one, sorry.
Yes.
In the paper, do they say how the nodes are informed of the total number of nodes in the graph? Because that can also be a problem.
Let me. I did not go through this entire paper because I focused on the gossip version, so I don't know, but it's a good question. I can look. So I don't know really.
Okay.
Anti-variate consensus.
Okay. And I have another question, which is, I think, about the Christophe and Grossi thing. So you said that if there is a cycle between gurus, then we want to take the majority vote amongst the guru
Yes.
as the vote for the whole group of people concerned.
Yes.
I wonder what was the rationale between that about that. Because, for example, if I have a cycle of gurus with 2/3 of yes and 1/3 of no, for example, I have the feeling that you can say, okay, let's just pretend that all the people that delegate their vote to the guru and the guru themselves have, in fact, a fractional vote of 2/3 in favor of the proposition and 1/3 in against the proposition. That would seem more natural to me, I think.
I mean, yes, but I think the idea that was that everyone has either 0 or 1, like the states accepted or rejected, I guess, and not 2/3. So I don't really. Yeah, I mean that's a good suggestion. But the idea was basically that we take the main opinion of the graph and of the cycle, sorry, and we propagate it to the followers. Not a fraction like. Yeah.
One on this model, one thing perhaps, I think, I mean, iterates of Boolean models have been studied. People who study idempotent algebras, I mean, so that, the Boolean is so belongs to. So they studied spectral. They use spectral analysis in different algebras. So you take the Boole algebra, you can pose eigenvalue or eigenspace problems, and there might be a classification. I mean, for other idempotent algebras, it was thoroughly studied, but there might be a classification of all periodic regimes and the structure of these periodic regimes using spectral analysis in non-standard algebraic settings, I believe.
Okay.
It happens if you play with, for instance, max plus or min plus. So you get these periodic behaviors, and you can interpret them as eigen properties, and you find the cycle analysis again. So there might be a way to do something similar here. It's a guess.
Okay. Yeah. Probably. Okay.